Yeah, okay. Uh, well, yeah. Today's talk is supposed to take 1 hour, but unfortunately, due to Zoom limitations, it's like now we are going to be restricted to 40 minutes. So the the work that I'm going to present here isn't really the work that I personally do, but just an introduction to infectious disease modeling. And what I thought uh, would be to put this for people who don't really know much about mathematical modeling and how important it is in solving some problems. So there isn't going to be much mathematics in this because the intention is to show people how mathematics can be used to solve the real world problems. So it's just sort of basic. But with time, we will come back here and then now do mathematics and now actually see it when time allows. Okay, right. Now, the most important question is, what is mathematical modeling? And based on the answer to this, we shall see its importance in real life. Now, I will start with some famous quotes from the great scientists. And around this 750 before Christ, Pythagoras said, all is number. I just took some short citations from these guys' works. So a number coming from mathematics. And then the Plato around 250 before Christ, he said, God always geometrizes. That also indicated that when he observed the laws of nature, he found that everything seems to be well shaped in a special way. When you construct a human being, when you construct a stone, then he wondered that, oh, wow, seems that God geometrizes everything. And then Galileo said, the book of nature is written in the language of mathematics. And without it, we find it impossible to understand a single word. And most importantly, without mathematics, we wander in vain through a dark labyrinth. So that really also persuaded the idea that mathematics is fundamental to every object or living being on the planet Earth. And this British mathematician, Alfred North, he also said, nothing is more impressive than the fact that as mathematics stood increasingly closer into the upper regions of ever greater extremes of abstract thought, it returned back to Earth with a corresponding growth of importance for the analysis of a concrete fact. And now the paradox is fully established that at most abstractions are the true weapons with which we control our thoughts of a concrete fact. So this British mathematician was also persuading the idea that all that we should somehow be thinking, or the way we do think, we think in a logical way, and that logical way is really written in terms of mathematical language. because our thoughts are not just haphazard in the space, but you think in a certain way to make an idea more feasible in mind. And similarly, James Jean, around this 1930, he also said the great architect of the universe begins to appear more and more like a pure mathematician. Well, for those who might not know, in mathematics we have two branches, applied and pure mathematics, where in the pure mathematics deals with the abstraction of important theorems that describes certain principles in life. So the basic foundation or formulation of those ideas are usually being described from the part of pure mathematics. So hence why he said now the great architect begins to appear more like a pure mathematics. The Bourbaki also said, who was also extending the Hilbert axiomatic methods, he said, from the axiomatic point of view, mathematics appears as a house of abstract forms, the mathematical structures, and it so happens, without our knowing why, that certain aspects of empirical reality feed themselves into these forms as if through a kind of pre-adaptation. So this guy, as he was proving or explaining some of the logical structures, he found that surprisingly, everything seems to be fitting into these axiomatic forms. And it was as if it was predefined before you move or try to describe a certain structure, you realize that, well, there is a certain form that it will exactly fit, no matter how new the axiom is or that structure. So it was like some kind of a pre-adaptation into it. The Eugen Wiggers also said the unreasonable effectiveness of mathematics is a wonderful gift which we neither understand nor deserve. So I think these are just some few quotes from great mathematicians, or of course, let's say great scientists who happened to overlap with mathematics in their careers. And also, this one I think everyone knows, Einstein, who also found mathematics as a very beautiful expression, that it was sort of like a religious understanding. And the most important is how we access, or what was strange about this reality is how our mind is able to access this um, religious understanding, which is more like you believe something is this, and then you try to pursue some proof, you realize that it is exactly as it is written in the book of nature. And okay, the last will be Paul Derek. He said, it seems to be one of the fundamental features of nature that fundamental physical laws are described in terms of physical theory of great beauty and power. He was the quantum physicist who also found that to describe certain physical laws, you only need mathematics to understand how those laws are being defined. And what was strange was that why is nature constructed in this along these lines? Why is it constructed in a way that we understand these um, physical laws through mathematics? And then he found that no, nothing we can do, but we simply have to accept that mathematics is central to this. Okay, now mathematical modeling really is a branch of mathematics where we use certain mathematical tools to solve the real problems. Actually, we have two big worlds, right? We have two big worlds. The first being the real world that we are living in, where we every day we experience some problems, we do some experiments. And now when we have those problems, you now migrate from the real world and get into the mathematical world. So when you are in the mathematical world, you start to build some theories behind what the real world or what you're observing in the real world. And you really completely forget about the real world. You simply get yourself absorbed into the mathematical world. When you get the solution, you will now go back into the real world and now interpret your solution in terms of mathematical understanding. So it's only between these two that we are able to understand certain problems. So when you're in the real world, nothing makes sense. But when you get into the mathematical world, you forget about the real world. You simply solve what is there and deal with the consequences and then come back. So that's where the applied mathematics comes into picture. Actually, we have many types of mathematical branches. We have economical mathematics, and we have fluid dynamics, mathematical biology, computer science, quantum mechanics, mathematical finance, and mathematical physics. And in all these major branches, of course, there are many types. Also, actuarial science is also within the computer science. So we use different mathematical tools to understand these or the problems emerging from these types of areas. And you will find most of the time that in mathematical economics, we sometimes use calculus to describe the rates of change or inflammations. Some sort of a group theory is also absorbed in the mathematical economics. We also, like in fluid dynamics and mathematical biology, we mostly use differential equations to describe certain processes and certain dynamics. Computer science relies mainly on number theory and also some sort of topological structures or topology. All these, as you can see, different tools that we use, like in mathematical finance, we use linear algebra a lot to understand certain processes. It is at this juncture that I would like to invite, for those that are not mathematical folks, to know that our department is well equipped with mathematicians from all these different branches. For example, mathematical finance, if you have a problem related to that, you can come to mathematics and Professor Mulachi will gladly assist you in those problems. And if we have a problem related to maybe biology, we have a group of mathematicians in our department. Ndatengaga Nkejani is one of them. Menoma Senegal is one of them. Ndatimu Tumelo is one of them. Of course, the one speaking with you is also one of them. So when you come to many other fields of mathematics, we have different expertise in our department. So if you have a problem, don't sit back, but just approach the maths department. And I can assure you, you will find appropriate folks to address your problem. So now, here is what is called a mind map. Things don't necessarily follow this map, but in general terms, we expect mathematical modelers to follow the same idea, right? Now, we have a problem or a scientific question that we would like to investigate. The most important thing, so this is like a road map, a mind map for both mathematical and statistical modeling, where you need to start by asking a question. You cannot do any research unless we have a question to answer. It's very important that you ask a question. And then you will have to collect appropriate data where applicable, and then do some statistical modeling. Now, you can test your model against some data, or you can, to do more robust modeling, you can build a mathematical model and then test that mathematical model against the data. When you are satisfied with this, or if you find that your data doesn't fit the model, it could be because of the question that you asked. So you might need to go back and ask a question or reframe it again and start all the process. Now, if you are happy with the results from your model fitting, then you can report back and give the solution to the scientific community or the human population. So this is just a general overview of a mind map for mathematical and statistical modeling. Now, in principle, we can now go in a detailed way to understand how statistical modelers are doing their modeling. Of course, we have the policymakers, which will be the government, of course. We also have action takers. We have basic sciences, clinical sciences, and all the social sciences. This is where the problems, usually not necessarily the problems, but what you are interested to find comes from. Now, the first thing that you do is to ask a good question. That means you now need to distinguish what is the real problem that you want to do from all these other branches there. And then you frame it in a statistical question, design an experiment, collect data, apply statistical tests, right? And then choose the appropriate model, test the model against the data, interpret the results, and when you are not satisfied with the results that you get, you go back and reframe the question and follow the process again. Only then, when you are satisfied with the results that you get, then you report back, you write a report and give back to the policymakers. So that's generally how the statistical modelers are modeling. Now, this is the roadmap for mathematical modelers. More or less like the statistical modeling, which starts with a good question, right? And then you frame it in a mathematical way that you'll be able to answer. And then you design an experiment. Designing an experiment, that means choosing the approach that we are going to use, whether we are going to use continuous models or discrete models or agent-based models. So then you collect data. If they're available, then you can build a mathematical model. And but at times you may not have the data. You may build the model from designing that, and then you build a model, test it against data if you have, or you can now take a model, decompose it into the small problem, whereby now you formulate the model inside another model. So that means now you try to decompose the bigger model into the smaller segment that you can easily solve, adjust, interpret the results, test the model, and then only at any stage as you can realize, there is always some sort of a way to go back and redo the whole process if you're not satisfied with what you get. But once the model fits the data well, then you report back to the policymakers or action takers. So this is just a general overview of mathematical modeling. And now, here is a full-blown mind map for statistical and mathematical modeling. In this, everything stays more or less the same, but what is most important here now is to understand the problem at a level of a pathogen. So, for example, now since we are attacked with the COVID-19, before you start modeling, you need to understand how that virus works. What is the replication cycle of that virus? How fast can it replicate? So you need to understand that from the pathogen level, and from the host point of view, which group of people can it affect? Can it affect animals, humans, and also the social behavior and political context? So that's the first thing that we do now in this general setting. You don't just wake up and start modeling, writing differential equations. You need to understand the problem from the level of the pathogen, host, and social. And then you follow more or less the same procedure, ask a good question, identify the real problem, and collect data and all that and all that. Now, what is most interesting to me is that your report now should give an evidence-based report. So you don't just say, well, this is what we find. You need to provide an evidence that such a thing does really exist. So hence why we say give evidence-based advice to policymakers and action takers. So that's why it's very important. As much as we wanted to build the COVID-19 model, but we are supposed to find the appropriate data so that we can train our model with that data to provide enough evidence of how the virus is going to spread throughout the population. So that's where the mathematical modeling comes into picture and comes into significance in understanding how the problem works. Okay, right. Now, this is just some process of mathematical modeling inspired by Brian Williams, who was the former director of African or intergoverning body of African Institutes for Mathematical Sciences, also for South African Center for Mathematical Epidemiological Modeling and Analysis. Now, he said, what is most important, the first thing you look for an interesting pattern. And you can only look that interesting pattern when we have the curiosity, right? And then now you invent stories to explain them. So that means now you need theories to explain the patterns that you see. Choose the simplest model or the best qualitative story. So that means now you want to test the hypothesis. And then work out the mathematical consequences of your hypothesis. That means now you solve the problem and tell what you find. That means you are now deducting solutions from your model. Now you have to interpret your deduction into the real world. Now explain what are those solutions that you have found. So it's important that after you get the solution, you report back into the real world, right? And then if you are happy, then you can design a way of collecting data and then test whether those predictions that you found are correct. When you're not happy, you start again from number one. And to do this, you only need persistence. Otherwise, you will get tired to go back to number one, looking for the patterns again, designing new experiment and all that. So it's only persistence that will lead you to that, and ultimately you get the good answer. So the question is really what makes a good scientist? I just want to throw this to you and think whether being a good scientist, we are a good scientists. Okay, so this is just an overview of the mathematical modeling. And now we can all right. Okay, now let's. Oh wow! What is this? Okay, well, the slides that I will present here are from my supervisor at the local course supervisor at Stellenbosch, Professor Juliet Podium, and I found them very interesting and very concise in trying to explain in general how to model infectious diseases. So, not to spoil the the, the presentations, I decided to bring them as they are. Right. Okay. What is this? Control L. Oh, Control L. Okay. Right. Now, this is basically where today's talk is all about. But I wanted to motivate why we are doing what we are doing by showing you the importance of mathematical and statistical modeling. And then now we can quickly go into the infectious diseases. And this is a broad topic, hence why I said I just brought these ones because they are very succinct and very short, just to give you an idea of how we do modeling of infectious diseases. Now, like in any field, we start with some terminology that you need to understand so that now we can be communicating easily. So we can talk about the exposure, whereby you are saying that someone is potentially, is at a state where he can be infected, not that they are infected, right? So there is some exposure between a parasitic organism and the host. And there is another stage we call infected, whereby and a parasitic organism enters the host. So, for example, here we would talk about now the COVID-19 virus now entering your body. Now, inside the infected, we have the infectious, where we now say once the organism has entered, now it starts replicating inside your body. And it is only at that stage that you either feel sick or not sick. But the moment the virus starts replicating inside your body, we now can say you are somehow infectious, or you are now in a position to transmit the virus to the next person. And then we can talk about the disease, whereby the parasitic organism causes the changes in the physiology of the host or the infected individual, affecting survival and reproduction. Now, well, though in many cases people use the word diseased as for dead, right? Whether they sometimes use it like you are diseased, but in general, we are just saying you are at that stage whereby that organism has now started changing the way you look, right? Maybe the face will start to shift, I don't know, but then we can say, oh yeah, with for the dead. Yeah, that's true. It should be C. Yeah, okay. Yeah, I think maybe because they look somehow familiar. Yeah, well, yeah, you're right, Prof. Yeah, that most of the people sometimes they use it, or in some papers when you read, they mean resist like you are dead, right? So that's right. No, that's really true. So I'm just saying, be careful. Some folks use it for that matter. But like when they design their model to represent the category for disease, they just you'll understand that they are saying that the person is dead, like they are removed, they don't care enough. But actually, it is not that, right?
Is it not the same as symptomatic, that they're showing the symptoms, or is it something different?
Yeah, basically. Yeah, starting or shading. Oh, we will also show here in the next slide that shading of symptoms. Okay. Now, of course, the infectious, well, where that is that state whereby we said you are now in a position to transmit the virus, if we are talking about virus, to the next person, right? Okay, now, as you might see, we have different levels. Someone gets infected, and then he may take some time before you realize that the person is infected. So there is some time lapse between infection and the onset of infection. And now, actually, what we normally say is that when you get infected, but you are not showing any kind of symptoms, we are saying you are in the incubation period. It's like that time when the virus is still replicating inside you, and then the moment it reaches a certain level, it makes you now show that you are really infected. And then it's only when it shows symptoms that many people start to look for clinical assistance. And then sometimes there is a time where you are infected, and then you are not showing symptoms. So the virus is like it is there, but not necessarily replicating very fast. And it was only at a certain point that's when now you start to show symptoms, or in fact, you start to become infectious. So that means now you are able to transmit the disease from you to other people around you. And similarly, this is more or less the same idea that people go different stages. Others they show symptoms, others they don't show symptoms. Like others they show symptoms when they are at a critical stage. Like now, once you show symptoms, you need medical assistance very quickly. Sometimes you don't show symptoms, but you are still infectious, which means uh, you are the onset shedding has started, that you start to feel not good, but you are able to transmit the virus or the disease to other people close to you. So now there are different types of mode of transmission, and the most common ones are the direct transmission, whereby we can talk of direct contact. When we talk of, obviously, COVID-19 would be when you touch an infected person or you touch the surfaces that are infected. Or when we talk of HIV, we will talk about sexual contact. So that's when the direct contact happens. And then we can talk about the droplets, where now the viruses are being exhaled to the environment, that now we can infect other people that are in direct contact with you. And there are so many other different types of transmission being indirect, whereby we can talk of airborne, maybe some sort of, you know, viruses being carried along by the air and start to infect people at a certain region. Or we can talk about vehicle-borne, where we transmit through the vehicles. Like now your car has some, like the rims, they might go over a certain infected region, and as they move, they might take the disease or the virus or pathogen to another region, and so many other types of transmission. Okay, now what also is also important is about our immune system, which also plays a critical role in fighting against diseases and spread of maybe unwanted pathogens. So we can talk about the active immunity, which requires stimulation of the antibody production, right? So the immune cells need to be stimulated against the presence of a certain virus. And it's only through the production of certain antibodies that the immune system is being cautioned or primed against the presence of such viruses or pathogens. We can also talk about passive immunity, where there are some antibodies in the body which are not necessarily being primed or stimulated to the prime immune system. Sometimes they, like now I hear at home there some people are going around infecting people for the what do you call common cold. So they give you that injection. It doesn't mean it's going to heal the common cold, but it stays in your body and fights it as it enters. So that will be more or less related to passive immunity. Okay, right. We in epidemiological modeling, we have two major branches. The traditional epidemiology, where we seek the what caused that disease outbreak, right? What happened? What caused this virus? Is it from animals? Is it from humans? What happened? And then how much can it cover? That means disease surveillance. How much has it covered? And that is usually done for the management point of view. And then we have the epidemiological modeling, where now we use mathematical tools to define certain principles, right? And then explain certain patterns. That means whether the transmission or the infection is going to lead to what is called epidemic or the pandemic. So we use the mathematical epidemiology to understand these, build the models. Models now are being used to predict the spread and then also used to control the infection. Right, so these are just some of those levels, whereby we talk of an endemic disease, whereby we just say there is some sort of infection or some disease in the population. And then epidemic, we will say, well, it seems to infect a certain number of people. And then now if it leads to a broader extent, then we will talk about disease outbreak. If it now covers a bigger portion of the population. And if you still cannot control that spread of the disease, then now it becomes a pandemic. So these are just the general terminology they use in epidemiology. Okay, so these are just some common sources that I will not go into because our interest is more on COVID-19. Right. How much time?
I can see one.
Okay.
Extend this next minute.
Okay. Now, part two, oh no, I forgot. Now in part two, we are just going to briefly show you how we now build a model, and then you can see how those mathematical models that I have been talking about are being constructed. Okay, right. What's this? Right. Oh, it's controller, is it?
Yeah, controller.
Okay. Okay, just like as I said, infectious diseases, we have those two major types of epidemiology. And this is the picture that we have seen previously. And now, in a simplified view, suppose we have one infected individual, right? And then we now try to see how we can adopt that general overview into a simple form. Now, when we only have one infected person, it might happen that the person is infected and at some point he becomes infectious. So that means he gets infected, but after a certain period, then he starts to be infectious. That is now the position where he can transmit. But because it's just one person, we sometimes don't worry about the symptoms or even the disease, right? So people like now, we are told that there is one guy in Lesotho who is infected, but people just went up and down. They never cared whether there is one person, or they never even cared about the COVID-19. So that's the problem of the simple overview of these epidemics. Okay. Actually, it might happen at some point that that infected person, once you get infected, then you become infectious. So these are another much simpler form. So when we assume that once you become infected, you are able to transmit that to the other people. So infected now is equal to the infectious. Now, while talking about that, we usually represent this by grouping individuals into different groups, where we have the susceptible population, people who can be easily infected, and then the infectious one, and then the recovered. Right? And now, obviously, the susceptibles, they move to the infectious class, and then the infectious, they move to the recovered class. So in any stage, we can now realize that the infectious are infecting the susceptibles, and then now we can now translate this into the health-related states, where we will now define in terms of variables and say we have S for susceptibles and I for the infected and R for the recovered. Sometimes people they call it removed, but removed just means that they have been taken away from the population, not necessarily that they they have recovered from the disease. Okay, it all depends on what kind of model you are building. Okay, usually the susceptibles are being infected at a rate beta, and then the infectious are being recovering at a rate gamma. So there are different rates whereby you transit from one population group to another. And in any stage, we can write the changes in the population at an arbitrary scale. It could be any scale that we would like to measure our change with. So hence why we will now write the as the tau, because tau can be any measure that we would find it appropriate to see major changes in the population. And then we can write the simple ordinary differential equations to describe the changes in this population, given that the susceptibles are being infected at a rate gamma or beta. Okay, right. Now, usually in this kind of modeling, we assume a closed population, whereby we say the total population consists of only susceptibles, infected, and the recovered. No other types of groups or populations that we regard. So we assume that our population is closed and is being constant. Now, in general, we usually describe this in terms of time, because time, of course, maybe is a basic scale for, or it's an important scale in measuring changes. So we usually want to say how many people will be infected over a certain period of time, hence why we regard now those changes in terms of time, and see still more or less the same differential equation, but now we explicitly say we regard this in terms of time. And now we can use our model to draw the phase birth rates, which are just the directories that are showing us what we can do to control the disease, right? So these are just the phase birth rate or phase diagrams, which shows how the infection progresses with time. When you're given the number of susceptibles and then the infected individuals, and then you try to find the rate of change of the infection. And the target mostly would be to find where there is no change in the number of infected individuals. So that means we would like the IDT to be equal to 0. And in that case, you realize that it will be more or less flat, sort of. Hence why many people, you will hear them talking about flattening the curve, which means they're trying to say, can we reach to the condition where the infection, there is no change in the number of infected individuals, right? Those that are infected, they just remain constant. We no longer have new infections. So this is what we can do to understand how we can now do this. Now, the question is now, how do we really actually flatten this curve? Because you can see it was sort of, skewed somehow, and then the target is to have it flat, right? Now, that's the bigger question. How do we do that? And that leads me to the next presentation, or the next slides, where we will talk about important measure that we often use. Oh, I forget all the time. Uh, you need to change this. No, in fact, you should uninstall it completely. Okay, right. Right. Okay, well, right. Okay, I will not talk much again about these ones. These are just a recap of what we have discussed. Right. Okay. Now, in principle or in general, or to I think what we saw with the first model where we have only susceptibles, infectious, and then the recovered, that was just a simple overview. But in general, we have different stages in between where you have the susceptibles, and then the person gets infected, but once infected, not yet infectious, right? So we can define that stage where we say the person is infected but not infectious. And we can now say it can move from being infected to being infectious. And we can also move from being infectious to the recovered. So in any case, we can use these flow diagrams to show us what is the transition from one class to the other, right? So that's basically that we assume that they are being infected at the rate gamma, and once infected, they are not infectious already. But after a certain time, which we said is the incubation period or latent period, then they become infectious. And then once they're infectious, now they start infecting the susceptible population, and so on and so on. So this is just the realistic, more realistic overview. To be more realistic, we should assume in general that at any stage people are dying. Of course, the susceptibles are dying. They are not waiting to be infected for them to die, right? So we assume that they die at some natural death denoted by mu. And for simplicity, we also assume this is the same across all the population groups, that is just the natural death. Because at any stage, it doesn't mean when I'm infected, I will die because I'm infected. I will die because it's my time to die, right? So hence why we still have the natural death, right? And then we can now describe this in terms of the state variables, where we have susceptibles, and then we say exposed, whereby you are being infected but not yet infectious, and then we can move from being exposed to infectious. And now we can, based on that, we can now write a system of differential equations to describe the changes in any of those group populations. So this is just a general overview where we assume the V is the birth rate, that obviously newborns are being born, and then they become susceptible, they die, they get infected, and all that. So I will not explain this model, but just a representation of what we have seen. Now, like as I said, our major interest is to say how are we going to flatten that curve. We do so by first looking at what is called basic reproductive number. Sometimes they call it basic reproductive ratio, which is the measure that shows how many secondary infections we will have from one infected individual when introduced in a completely free, disease-free population. So that means this measure tells us, like, now we do not have COVID-19 with us here. Someone who is infectious comes into this room, and we want to see how many people can he likely to infect. So we want, and that secondary infection, we are going to find it by using this number called R naught. And to do that, we usually need to find the rate at which an infected individual produces new infections in a live population. So how many people can you likely to infect, right? So if, well, we want to count, like looking at the chances that in a group of maybe 1,000 people is it's not easy for a certain period that I can infect all of them at once. There are a number of people that I can likely to infect. So we need to find that. And we also need to find the portion of new infections that became or that becomes infectious. So, well, like I said, we said some people they get infected, but they do not become infectious. So we need to find how many are those that are actually infectious after being infected. And then we also multiply that by the duration of infectiousness, like how long has the infection period happened, right? So once we have that, we multiply these rates, and then we find that number that is called basic reproductive number, which is going to tell us whether this disease is going to spread or not spread, right? So what is important about this is that if R naught is greater than 1, in principle, it means the infection is going to progress throughout the population, is likely to progress, right? And when R naught is less than 1, it means over time the infection is going to be diminished. It does not mean it will go instantly at 0, but it tells you that with time the disease is going to die out. So that's when R naught is less than 1. So hence why when we are using that R naught, we can be able to see how we can flatten our curve. So basically looking at these rates, we can adjust our model in such a way that now we want our basic reproductive number to be less than 1. Now, for this model, the basic reproductive number is given by these products of these rates. So, as in how you calculate it now, well, it doesn't matter. But this is what it is. There is a course here we call mathematical modeling. Well, that's where we can learn how to compute these from given this model. But what is most important is that we can always find this from our model, and then now calculate this, and then see whether when we're given certain parameters, we can be able to find what that R naught is. And we also need to find the equilibrium states or steady states, because with it now we will be able to find whether the disease can be endemic or pandemic, right? So the disease equilibriums, like as I said, given the parameters, now we can calculate our R naught. So these are just some examples of what mu and alpha and everything can be. And then now given these rates, we can calculate our R naught. And also where there is availability of data, we can now feed our models to the actual data and see how is the disease progressing with time. So this is just an example of the measles dynamics. So then we feed our models to describe this, and then given some information about those parameters, we can now calculate what will be the likelihood of achieving less than 5,000 or what do you call it, 500,000 over a given period of time. So this is just an example, and that we can also use more or less the same to understand the COVID-19 pandemic. Okay, I would like to stop here for now, and thank you very much for your time. And
I'm not sure if there are some questions that we can in.
We have questions from the online models that you see. Actually, with respect to the ongoing pandemic, the models are they're just terrible in terms of predicting the outcome. Just terrible. I mean, I think even the latest one, I think the South African one, I think was the one in the predictions by September. So it seems the assumptions that they make, it's more of like a scavenging. I don't know why is it that they always getting called.
Okay, maybe because we also have the online community. I'll just try to repeat your question so that you could understand. I don't think the question. I think your question was what is the cause for the models to be out of touch with reality?
Yes.
Okay, thanks. I just want them to understand what the question was so that you get the response.
Okay, well, one can always say the fundamental question relies on the assumptions that have been used to build such models. It doesn't really mean models are wrong, but the assumptions that the modeler might have embedded might be the one that are leading to those strenuous um, outcomes. So I still say with this modeling, we can still predict exactly the right number given the appropriate information. So the models are not wrong, but the assumptions, they may not be wrong, but they might be too simple. Hence, if you put simple assumptions, then you are likely to get unrealistic results. So I think my answer really depends on the assumptions made about the model.
For us, the big I heard from the news that they said it would be cooler, but it will be something else. Or it's who did it.
I think also the data that was available from initially there was a lot of data and stuff, but now they have quite enough data to create precise predictions. But this process, I don't know how
it's not only South Africa. I mean, all the models, even in the US, they keep on changing. It's not like big models putting the assumptions. Because they will say, like the model predicts you're going to have 200,000 deaths by maybe next week. And then they start, having new infections. And then all of a sudden they change it quickly. No, it's no longer 200,000, and maybe 50. So how do you trust the model? For me, I mean, we just talk infections, but I don't trust the model.
in terms of quantity, it's very, very difficult to, because the one for years, the first time they became 100,000, but they had also conditions that provided that people can continue with these conditions, which is very, very difficult to control. That people will continue like that. So you have to keep updating your model.
I was also going to add to that point that actually in most cases you find that they also do the scenario modeling. They're saying this will be the situation if the business is as usual. This is the worst case. This is the best case. So in some cases you might find that people are focusing on the business as usual model, but things change. For instance, they are saying if there's no lockdown, this will be the condition. But if you enforce lockdown, it means it's no longer business as usual. So that business as usual model doesn't work anymore. I think they also do that scenario modeling. or at times they might say, okay, this is the worst case scenario, but we find that there are some interventions that actually make the situation much better. I think that's contribution.
Yeah, well, I understand.
There's also another question from Dr. Matesi. He's at CSIR, but he's asking online. Actually, there are two questions. The first one is, how easy is it to get this rates for new diseases like COVID-19? Then under what time scales and spatial scales can you assume you have a closed system? I think the first one is, how easy is it to get so the rates like are not for disease like COVID-19 is the first one. You can address that one first, and then the second one is about the time scales.
Well, the truth is that it's not easy to get these rates, and the reason being, we can find these rates more robustly when we have data. When we have good data, then we can find these rates that we use in our models. But where there is no data, we will rely on the biological information that we know. For example, of how the virus spreads from one to another. We might use certain assumptions from different virus rates. So for COVID-19 is very difficult because of the availability of data.
I think it's clear. The second one is about under what time scales and spatial scales can you assume you have a closed system, like maybe n is constant? I think that's a question. Under which
Okay, I will throw this to I think I got a question. Yeah.
the question. Okay,
Okay. Okay. Under what circumstances can we assume closed? Well, we can. The reason is, well, when we have, for example, when we apply quarantine measures, if we assume that no one in this room goes out, then we assume that the population that is going to change here is only based on that. But like, for example, when we assume that there is no one coming outside from South Africa to Lesotho, then we can assume a closed population. So hence, of course, we assume n is constant in that case. So, but where you have a Basotho living in peace and someone comes through their leverage, comes in continuously or not continuously, but he has the opportunity to come inside, then we might use that special modeling point of view that, well, there's that movement there, hence why n will be constant. Because what comes in, we can assume.
The reason that we keep on going, because even now the scientists are not really sure how it's transmitted. Remember when it started out, they thought if you are symptomatic, you will transmit. But then the rates of infection will really high. So that's one of the things we assume if, let's say, it's a closed system, is it airborne? There are a lot of other elements that the virus put. That's why they will make it capacity that even now they're not really sure how it's transmitted. At least they don't know if it fails.
Okay, I would like just for the online community just to say we appreciate and acknowledge Dr. Matesi's question, but we would like to say, in fact, it's not me, but the whole house here feels that those are the difficult questions, really. They are very difficult to answer. So we might try to answer them as we did, but we should accept that those are difficult questions, as Dr. Maduna has just said, that is still not clear as to how the transmission occurs. So that's really what makes it extremely difficult to answer those questions.
Okay, thanks very much. I tried to ask them. I'm not sure if they still have questions. If they do, they can still raise their hands or pose the question. Okay.
Is it possible you can go to your last slide?
Mhm.
There was the slide about measles.
Okay.
Yes, with the curve.
Mhm.
And if I've made a mistake, then there will be no question. Uh, yes, you said this graph is the persistence of measles, or at least it says down there, pre-vaccination era. And you said there's this relationship between action something and mathematicians who are modeling this and this. And I'm assuming this graph itself was modeled by a mathematician. Does this graph not say the incidence of measles is going down over time?
Yeah, that's what is trying to.
And if so, why do they vaccinate measles? Or am I wrong? Could you please explain the graph a little bit, because I thought that's what it's saying.
Why do they vaccinate?
Yes, because it looks, if I'm correct, it looks like the prevalence of measles, well, measles is not becoming as prevalent as time goes on.
So your understanding is that by assumption it will stay.
It will die out
with time.
with time.
Yeah, not really. Not really, because um, this is just based on the data that was collected over this period from 19 something 14 to 1960 something, from 44 to 67, right?
Right.
So by having a trend that goes down, it doesn't necessarily mean that it is going to die out with time. Like you give it 100 years, it will, because there could be some times where we have an unexpected rebound. Sometimes these things they call them outbreak again. So it's only the trend within that period that is like this. But as you can see, it hasn't quickly gone down to zero. So hence why we still need to put those vaccination strategies.
Or perhaps maybe I'm reading this graph the wrong way. What's on the x-axis? Because now I'm beginning to think it's not time. What's on the x-axis?
The x-axis, let me remember. I think more or less like you know number of individuals.
And what's on the y-axis?
The y-axis
It says
is
something per year. I can't see that way.
Yeah, yeah, fade out, I don't know, fade out.
Yeah, maybe I'm not reading the graph properly because I thought it was time in the x-axis.
Oh, okay.
And okay, so maybe I am interpreting it wrong.
Okay, okay, okay.
Can I just read some comments from the online community, those online? And Dr. Lebusetsa, the lady, he doesn't like being called doctor. Dr. Lebusetsa, the lady, he says, thank you, Tate, interest in talk, learned a lot. Pity too much maths for me. He's a chemist, so I don't know why And then Dr. Madesi came back and said, thanks, Dr. Mahasa, I think you have given valuable insight. So these are just the comments. There's no question. No, it's like there are also no questions here. So I think we should give you the last round of applause.